This is the brief on isentropic gas flow and its consequences. Okay, so we're exploring the physics of gas flow, specifically this ideal state called isentropic flow. And this concept is really the foundation that defines both basic physical phenomena, like sound waves, and the absolute theoretical limits of engine efficiency. First, let's define what this ideal state even is. Isentropic flow is a process that's both adiabatic, meaning no heat is transferred, and it's also completely reversible. For an ideal gas, this is all defined by the adiabatic gas law, which basically just says that pressure times volume raised to the power of gamma is always a constant. Second, and this is the really cool physics result, when you take the equations that govern this perfect flow, they're called the Euler equations, and you linearize them, you literally get the classical wave equation. And that equation? It specifically describes sound waves as waves of pressure. What's crucial is that the math also defines the speed of that wave. Yep, the speed of sound itself. And finally, let's talk about the real-world metric. See, isentropic flow is the absolute ideal baseline for propulsion systems. It gives you the maximum theoretical exit velocity and thrust because the stagnation pressure stays perfectly constant. But in the real world, things like a normal shockwave can happen, and bam, that stagnation pressure drops instantly. This loss is the definitive metric for inefficiency. It's a catastrophic loss of energy, and engine performance just tanks. So isentropic flow sets the theoretical maximum for things like sound speed and thrust, while stagnation pressure loss precisely measures how far real-world systems fall short of that ideal.